All right, I think this will be our final video. We're on slide 32. So this is where we get into forces and circular motion. And again, this is another complete chapter in physics. So I'm just gonna kind of barely touch the surface, but basically just knowing, and we've already kind of talked about this, that if you're taking something and you're changing its direction, then it is considered to be accelerating, even if it's going at the same velocity. We talked about that when we were talking about acceleration earlier on in the chapter. Well, when things make a circular path, they kind of have some different things happening to them. First off, there's some centripetal force that's kind of pulling towards the center. And really, if I was in class right now, I would have this I use a remote that I have on a string, or think of like a ball on a string, and take your hand on the string and then you twist around the ball. So the ball's going like this in this circular path, and you're holding on to this string like right here. So this is your hand. And what's going to happen is this ball is just going to continuous around in this circle, right? Well, you are causing that force, okay? And you're in the center of it. But if I let go of this, if I let go of the string altogether, the ball, is it going to keep going in a circular path? Actually, no, it ends up going in this straight line path. So every point that it's at on the circle, it's wanting to go straight line. But because of me, I'm forcing it, right? Actually, I shouldn't have drawn it like that. I should have drawn it like that. I'm forcing it to go towards the center, okay? So there are some other terms that you should know, because it's accelerating and because it's going in this circular motion. It has centripetal acceleration that's happening, because it's changing direction. Centripetal force is acting on it. Centrifugal force, so like, have you ever ridden the ride at the fair, or I can't remember, I might be older that they don't even have this ride anymore, but it used to turn around in a circle and it would kind of go up a little bit on the side, and you felt like you were stuck to the back of the ride. That's centrifugal force, which is sort of this outward tug. Even if you remember getting on those merry-go-rounds at the park or something, you always felt like you're going to fly off. In fact, some kids did, and that's why they don't have them anymore. Okay, and if you did fly off, you wouldn't be going in a circle, you'd be going straight. All right, so that gets us into Newton's law of gravitation. So Newton's law of gravitation just says that there's an attractive force between all masses. So even between you and your bed or whatever you're looking at right now. And why aren't we just being like magnetized towards each other then? Well, it's because of the proportionality of it. Earth is so big that it's going to attract overall. Okay? So proportional to the product's masses, and basically inversely proportional to the distance. Okay? And I think I did miss an example. We'll go back to that here in a minute. But on this one, I want you guys to go ahead, and because it's not going to give us the equation on here, I want you guys to go ahead and write this equation on your PowerPoint. Okay, so this is the universal gravitation constant. This is mass 1, mass 2, and this is distance squared. Okay, and a lot of people miss that square, and then it ends up making everything wrong. So you got to make sure that you don't forget that square. Okay? And this universal gravitation constant right here, this is something that would be given. All right, so it's 6.67 times 10 to the negative 11th Newton meters squared per kilogram squared. All right, we're going to do an example with that here in a minute. And I want to go back really quick because we forgot a couple of equations that we need to write on this page as well. And there's only a couple like this in the homework, okay? And I'm not going to get too crazy on this on the test. I mean, it could be on the test, but it would be pretty simple, okay? Very similar to the examples that we're going to do here in a minute. So this is centripetal accelerations equation, and it's velocity squared divided by the radius of the circle that you're making. And then this is just a force equation again, but it's dealing with when things are going in a circle. When things are going in a circle, then you kind of have to, again, involve this radius. So you have to square the velocity, multiply it by mass, and divide it by the radius. All right, so let's do an example. Let me pull up my notes here really quick. Actually, I gotta pull up my book, don't I? See if I can go on to the next section. Okay, and then do it like that. All right, so we're on example 2.16. All right, and this says that a 0.25 kilogram ball is attached to the end of a 0.5 meter string and moved in a horizontal circle at 2 meters per second. What is the net force that's needed to keep the ball in a circular path? Okay, so it's telling you everything you need to know here. It's telling you that it's going in a circle and it's asking you to find force. So that's a pretty good clue that you need to use this new equation that we just, used. All right, so I'm going to bring this down and just sort of plug in. So we got 0.25 kilograms times the velocity squared divided by this radius. And notice that it did say that, and in this particular example, it said that the ball was on the end of a string of a 0.5 meter string. But if you're holding it, and you make a circle, then that is going to be the radius, the whole length of that ball string. So, all right, whenever you go to calculate this, you end up getting the number 2. But I just want to show you really quick on the units. So you've got kilograms times, and when you square this 2, you also square the meters per second. So you end up with meters squared per second squared divided by meters. Well, because of that meters, it's going to cancel one of those. So you end up with kilograms times meter per second squared, which is the same thing as a Newton. Okay? And yep, we only need one significant figure because of that 0.5. All right? So that's a good example of how to do something that's talking about force that's involving circular motion. All right, so now I'm going to go on to the next page where it starts talking about, nope, didn't want to go to the previous. I want to go to the next. It starts talking about Newton's law of gravitation. We'll look at example 2.18. Okay, so it says, what is the force of gravitational attraction between two 60 kilogram students who are standing 1 meter apart? Okay, so So anytime it says something about the force of gravitational attraction, it's wanting you to use this huge equation, all right, that we did on that one slide. Okay, so this is where you need to use your constant. Multiplied by 60 kilograms. They're both 60 kilograms, so that's the same thing. And it says that they're how far apart? 1 meter apart. Okay, and that's squared. All right, so you've got to make sure that you plug into your calculator correctly. And at this point, you know, hopefully we've been in class and we can kind of, hopefully we've gotten our calculators figured out at this point, because really that's what gets my physics students, it gets all of my students the most, is just calculator errors. So you end up with 2.40, I need to add that 0, times 10 to the negative 7th newtons. All right, so that negative 7th right there tells me that's a very weak force. All right, so why? Because Earth is pulling much, much stronger on us, okay? And that's why we don't really feel that force between each other. Now, if Earth wasn't involved, then we would, okay? But we really don't because of Earth there. Now, I do want to show you example 2.19, because it kind of proves how we find gravity, like the 9.8 number. Sorry, my throat, I think I do these videos and then my throat gets like sore. You know, I haven't been teaching because I'm on summer break right now doing this, and so my throat's not, I don't know, where it normally is. All right, so this is saying that the surface of the Earth is approximately 6,400 kilometers from its center, okay? And if the mass of the Earth is 6 times 10 to the 24th kilograms, what is the acceleration due to gravity? So this is wanting us to actually find little g, okay? So what you do here is you've got force, kind of have this equation that we had earlier, but we know that force is equal to mass times acceleration or gravity from previous equations. And if we want to find little g, then we can divide both sides by mass. Well, that's going to cancel one of those masses out. So we're left with this universal constant times the mass of the Earth divided by its radius or its distance squared. Okay. So the problem though is that it gave us the distance in kilometers, which really we probably need to have that in just meters. Otherwise, we're going to end up with some funky units. So if you have 6,400 kilometers, you have 1 kilometer is 1,000 meters, you end up with 6.4 times 10 to the 6th meters. Okay, so you just kind of have to do that first. Okay, I'm not going to add all those units. Well, I guess I can. Just squeeze it on there. The mass of the Earth. Got to multiply by the mass of the Earth here. Okay, I'm going to rewrite this because I don't really like that. So 6.67 times 10 to the negative 11th, the Newton meter squared per kilogram squared, times the mass of the Earth, which is 6.0 times 10 to the 24th kilograms, divided by the distance squared. And that is going to, if you do all the math there, that's going to end up giving you 9.8 meters per second squared, which is what we use whenever we're finding, stuff that involves gravity. So this example right here was pretty intense, okay? It's really just a good example to show you how gravity is found and prove why, we use 9.8. All right, go back to my PowerPoint really quick. We did that. And the last little bit that it talks about is Earth satellites, and kind of just, they're going around in circular motion, and anyway, they're orbiting, right? We kind of hopefully have known or heard of that term before, which is just a term used in circular motion. And it's really kind of interesting because they're put at a certain spot that they don't go off into space, but they don't come back into Earth, because Earth's gravity is pulling it, but space is also pulling it out. So it's put in a specific spot that it just keeps orbiting Earth, which is pretty cool. And then last, weightlessness. It's saying that astronauts appear to be weightless but are still affected by weight. Really what's happening, it's kind of like we talked about with the moon. If there's no gravity there, then it's sort of almost like they're weightless. But really they're sort of just in a free fall situation. So if you were falling through the air, if you were skydiving or something, you were falling through the air and you try to take your weight, you would have no weight. So astronauts are considered to be in constant free fall. All right, and that's the end of Chapter 2's PowerPoint. So I'm going to stop the video and we will